Hello, my name is Mark Lonsway, and today I will be walking you through and teaching math concepts surrounding question number 8 on page 184 of the McGraw-Ryerson Calculus and Vectors 12 textbook. The problem states, a pollutant has been leaking steadily into a river. An environmental group undertakes a cleanup of the river. The amount of pollutant in the river t years after cleanup begins is given by the equation n of t equals 0.5t plus 5 over 10t plus 1. The first part of the question asks what quantity of the pollutant was in the river when the cleanup began. In order to solve the first part of the question, we must first learn a bit about combination of functions in order to solve what the question is asking. A sum of functions is the type of function that can be expressed through the formula f of x equals g of x plus h of x, where f of x is the output of the function, x is the input of the function, g of x is the first of two functions being added together, and h of x is the second of two functions being added together. To solve the first question, I have outlined a set of steps. Step 1 is to highlight key ideas from the problem. Step 2 is to input the value of t into the function given. Step 3 is to summarize our findings. The problem gives us the function n of t equals 0.5t plus 5 over 10t plus 1. As shown on screen, where n of t is the output of the function, t is the input of the function, 0.5t is g of x, and 5 over 10t plus 1 is h of x. Going back and highlighting key ideas from the problem, we are given the function that represents the amount of pollutant. We know that t represents the time in years after cleanup begins, and we see that the question is asking for the amount of pollutant in the river when the cleanup begins. Applying what we know to what the question is asking, we want to know the amount of pollutant, or n of t, at t equals 0 years. When we input the value of t into the function n of t, we get a value of 5, or in this context of the problem, the amount of pollutant in the river when the cleanup begins is 5. This can also be seen on the graph where there is a y-intercept of 5. We will then summarize our findings by saying, therefore, when the cleanup of the river began, the amount of pollutant was 5. Next, we will move on to the second part of the question. The second question asks, when is the quantity of pollutant at a minimum? What fraction of the original quantity of pollutant has been removed at this time? The question given to us will relate directly to the unit derivatives, more specifically the lessons derivatives of polynomials and the lesson of the power of the function rule. To solve this question, we must first highlight key ideas from the question. Next, find the derivative of n of t, then we will find when the pollutant is minimized by setting the derivative to 0. After that, we will solve for t, then input t into the original equation to find what fraction of the original quantity has been removed. And finally, summarize our findings. Looking at the question, it is asking for at what time the quantity of pollutant is at a minimum. Therefore, we will be solving for t when the rate of change of the pollutant is at a minimum. Before we start solving, I must first talk about derivatives and how to find derivatives through the power rule and the chain rule. A derivative is an equation that models the instantaneous rate of change at every point on the function where the original function is continuous. To find when the derivative is minimized or maximized, you must look for when the derivative is at the x-axis, or in other words, set the derivative equal to 0 and solve for x. This is because when the rate of change of the original function is 0, then there will be a turning point. In our case, for the problem, we must find the derivative of n of t, called n prime of t, then set it equal to 0 and solve for t. But first, we must learn how to find the derivative of our given function. The first step to finding a derivative is putting the function from good form to power form. Good form refers to when a function has no negative exponents on the variables. For reference, n of t is in good form. Power form refers to when rationals and radicals are expressed as powers. To put n of t in power form, we must bring the bracket 10t plus 1 onto the numerator by putting it to the exponent negative 1. Now that our function is in power form, we may now take the derivative. To take the derivative, we will now call the function n prime of t, so we know that it is the derivative of n of t. The next step will be to take the derivative of g of x by using the power rule. The power rule is a rule in calculus that is used to differentiate functions in the form f of x equals a times x to the exponent r, where a is a coefficient of x is the input of the function, and r is the exponent of x. The rule states that the derivative of f of x is a x to the exponent r is f prime of x equals a times r times x to the exponent r minus 1. For the function g of x, we see that the exponent of 1 gets brought down and the exponent on t goes to 0, which makes it equal to 1. Therefore, the derivative of g of x is g prime of x equals 0.5. For the second part of the function, h of x, we cannot use the power rule because h of x is a composite function, so we must use the chain rule. The chain rule can be used for differentiating composite functions in the form g of h of x. A composite function is created when one function is substituted into another function, or in other words, when you are given the function of a function. In the problem given, h of x can be expressed as h of m of x, as seen on screen. The chain rule follows the formula: the derivative of the function f of x equals a times g of x to the exponent n is f prime of x equals a times n times g of x to the exponent n minus 1 times g prime of x, where a is the coefficient of g of x is the function substituted into f of x, and n is the exponent of the function g of x. For our case, we can see that the exponent of negative 1 gets brought down, and the exponent of g of x is subtracted by 1 to get negative 2. And this will be multiplied by the derivative of the bracket, which in this case is 10. We know this because of the power rule as previously discussed. After simplifying and putting h prime of x into good form, we see that the derivative of h of x is h prime of x equals negative 50 over 10t plus 1 to the exponent 2, as displayed on screen. After all the differentiation, we see that the derivative of n of t is n prime of t equals 0.5 minus 50 over 10t plus 1 squared. As shown on screen, n prime of t models the rate of change of n of t. As previously discussed, we must now set the derivative equal to 0 and solve for t, which after some simple algebra and using the quadratic formula to solve for the roots of the derivative, we find that t equals 0.9 and t equals negative 1.1. These minimum values can be seen on the original function of n of t. For the context of this problem, t represents time, so our negative answer would not make sense for this problem, which leaves us with the answer of t equals 0.9. The next part of the question asks for how much of the original pollutant was removed. To find this value, we will substitute our value of t, which is 0.9, into the original function n of t to find out how much pollutant is in the river at this time. When we substitute 0.9 in for x, we get an output of 0.95. The question asks for what fraction of the original quantity has been removed, so we must find the answer in terms of a fraction. We know our original amount of pollutant at t equals 0 is 5, and we know that the amount of pollutant at t equals 0.9 years is 0.95. Therefore, since we know how much pollutant is in the river at this time and the original amount, we can say the original amount subtract the current amount, then divided by the original amount should get us the fraction of the original amount that has been removed. This gets us a fraction of approximately 4 over 5. To finish the question off, we must now sum up our findings by writing two therefore statements. We will start by saying therefore the quantity of pollutant is at a minimum at 0.9 years. Our second statement will be therefore 4 out of 5 of the original pollutant has been removed at t equals 0.9 years. The last part of the question asks what may have happened at this point. To solve this question, we will look at the graph on Desmos and use this information to infer what may be happening at this time, then summarize our findings. Looking at the graph of the derivative at t equals 0.9 years, we see that the rate of change is increasing. Therefore, we can infer this to either be the rate of leakage is increasing or the rate of cleanup of the environmental group is decreasing. We will sum up by saying therefore at t equals 0.9 years, either the rate of leakage of the pollutant has increased or the rate of cleanup has decreased. Applying this concept to the real world, a career that would deal with similar problem would be a pollution control technologist. Pollution control technologists focus on identifying pollution sources, monitoring pollutants, and addressing issues of contamination and pollution. They will often analyze the pollution levels of different regions like air, land, or water to find out how to attack the problem at hand. Oftentimes, they will use graphs to show the levels of pollutant over time, as well as monitor rates of pollutants entering the system, which is what we've done today. To summarize what was done today, we looked at the problem that dealt with levels of pollution of a river and found the level of pollutants at the beginning. We also found when the pollutant was minimized through the derivative of the function, then found what fraction of the original pollutant was removed. After that, we used our knowledge of graphs to infer what was happening at that point in time, then found a career that dealt with similar problems in a pollution control technologist. That's all I have for you today. Thank you for listening.